Municipal solid waste incineration ash applications. Incineration of municipal solid waste is a common practice to reduce the volume of the waste to be disposed in a landfill. Municipal solid waste incineration ash applications. Incineration of municipal solid waste is a common practice to reduce the volume of the waste to be disposed in a landfill. MSWI ash is the reuse for civil engineering purposes, that is bricks, asphalt, mixes, concrete and as fill materials. Incineration ash can be mixed with soil, lime, cement or concrete, which improves their physical properties. MSWI bottom ash as a substitute of aggregate in asphalt mixtures sub-base material for road and embankments applications is becoming popular amongst researchers. Objectives of the presentation: to know and understand the design procedures of sewers, to know about different types of sewer available, to know about the various type of material used in construction of sewers, to have a detailed knowledge on construction of sewers. Presentation outlines: shapes of sewers, design criteria of sewers, sewer materials, design of sewer or separate and combined systems, numerical and design of sewers, construction of sewers. Design criteria of sewers continued. Design, discharge, design to discharge, design to velocity. Design criteria of sewers continued. Design period 20 to 30 years. Design period is 20 to 30 years. Specific gravity of sewage. Sewage consists of 99.9% water. Specific gravity is nearly equal to 1. Then velocity of flow. Velocity of flow must lie between self-cleansing velocity and limiting velocity. Cam shield formula. V is equal to under root 8 beta S minus 1 into GD by F under root, where V is equal to self-cleansing velocity. V is equal to self-cleansing velocity. Beta is your dimensionless constant whose value depends upon the characteristic of sediments present in the Wisbech friction factor. S is equal to specific gravity of sediments. G is equal to acceleration due to gravity. D is equal to diameter of solid particles. Minimum velocity, also known as self-cleansing velocity. It is the velocity at which the solid particles will remain in suspension. Criteria for determining minimum velocity. For combined system, self-cleansing velocity is 0.75 meter per second. Owing to Baldwin-Latham self-cleansing velocity depends upon the diameters of the sewers. Self-cleansing velocity, diameter centimeter, 15 to 25, velocity meter per second, 1.0, diameter centimeter, 30 to 6, velocity meter per second, 0.7, diameter centimeter greater than 60, velocity meter per second, 0.6. Maximum velocity, also known as limiting velocity, velocity above which scoring or erosion of inner surface will occur. Scoring mainly due to abrasive action of harder materials like sand, grit, gravel, etc. Limiting velocity depends upon the material of the sewer. Sewer materials: vitrified tiles, limiting velocities 4.5 to 5.5. Sewer materials: cast iron, limiting velocity 3.5 to 4.5. Stoneware 3.0 to 4.0. Cement concrete 2.5 to 3.0. Ordinary brick lined 1.5 to 2.5. Earthen channels 0.6 to 1.2. Minimum sewer size, not less than 15 cm. Recommended size is 20 cm. In hilly areas, it may be 10 cm. Standard pipe sizes are 20 cm, 30 cm, 35 cm, 40 cm, with increase of 5 cm up to 2 meter. Sewer grades. It is the slope at which sewer is laid. Generally follows the natural slope of the ground, not steeper than 1 in 20. Slope of 1 in 40 to 1 in 80 for house sewer connected to public sewer. Gradient for self-cleansing velocity of at least 0.6 meter per second is presented in table 3.3. Minimum gradient. Diameter of sewer centimeter 20. Gradient 0.003. Diameter of sewer centimeter 30. Gradient 0.002. Diameter of sewer centimeter 45. Gradient 0.0015. Diameter of sewer centimeter 60. Gradient 0.0008. Then 75 centimeter 0.0006. 100 0.0005. Hydraulic formula. Chassis formula. V is equal to C under root RS, where V is equal to velocity of flow, C is equal to chassis coefficient, R is equal to hydraulic mean depth, S is equal to slope or gradient of sewer. Different formula for calculation of chassis coefficient. Cutter's expression. C is equal to 23 plus 0.00155 over S plus 1 by N over 1 plus 23 plus 0.00155 over X into N over under root R, where N is equal to roughness coefficient. Bayesian's formula. C is equal to 157.6 over 1.81 plus M under root R, where M is the Bayesian's coefficient. Hazen-Williams formula. V is equal to 0.849 CHR into R raised to 0.63 into S raised to 0.54, where CH is the Hazen-Williams coefficient. Manning's formula. V is equal to 1 by N into R raised to 2 by 3 into S raised to 1 by 2, where Crimp and Bruch's formula. V is equal to 83.47 into R raised to 2 by 3 into S raised to 1 by 2. Manning's coefficient N. Conduit material. Condition of interior surface. Salt clay stoneware. Good 0.012. Manning's coefficient. Fair 0.014. Cement concrete. Good 0.013. Fair 0.015. Cast iron. Manning's coefficient. Good 0.012. Fair 0.013. Brick unglazed. Good 0.013. Fair 0.015. Asbestos cement. Good 0.011. Fair 0.012. Plastic smooth. Good 0.011. Plastic smooth. Fair 0.011. Hydraulic elements of sewers. Most commonly used sewers are circular. Hydraulic elements for different flow conditions are presented below. Hydraulic elements of sewers. This is diameter D, this is O, this is theta, this is D. Circular sewers running full. Area of flow section. Area is equal to pi by 4 D square. Wetted perimeter. P is equal to pi D. Hydraulic mean depth. R is equal to A by P is equal to D by 4. Manning's formula. Velocity of flow. V is equal to 1 by N into R raised to 2 by 3 into S raised to 1 by 2. Discharge. Q is equal to AV is equal to A by N into R raised to 2 by 3 into S raised to 1 by 2 is equal to 0.3116 by N into D raised to R 8 by 3 into S raised to 1 by 2. Circular sewers running partially full. Center theta is given by cos theta by 2 is equal to 1 minus 2 small d by capital D. Depth small d is equal to capital D by 2 minus capital D by 2 into cos theta by 2 is equal to capital D by 2 into 1 minus cos theta by 2. Proportional depth small d by capital D is equal to 1 by 2 into 1 minus cos theta by 2. Area A is equal to pi by 4 d square into theta by 360 minus d by 2 into cos theta by 2 into d by 2 sin theta by 2 is equal to pi by 4 d square into theta over 360 minus sin theta by 2 pi. Proportional area is equal to small a by capital A is equal to theta by 360 minus sin theta by 2 pi. Wetted perimeter. P P is equal to pi d into theta by 360, small p. Proportional perimeter is equal to small p by capital P is equal to theta by 360. Hydraulic mean depth small r is equal to small a by small p is equal to pi by 4 d square into theta by 360 minus sin theta by 2 pi over pi d theta by 360 is equal to d by 4 capital D by 4 into 1 minus 360 sin theta by 2 pi theta. Proportional hydraulic mean depth is equal to small r by capital R is equal to into 1 minus 360 is equal to 1 minus 360 sin theta by 2 pi theta. Velocity of flow small v is equal to 1 by n into r raised to 2 by 3 into s raised to 1 by 2. Proportional velocity is equal to small v by capital V is equal to capital N by small n into small r by capital R whole raised to 2 by 3. Taking capital N by small n is equal to 1. V small v by capital V is equal to small r by capital R whole raised to 2 by 3 is equal to 1 minus 360 sin theta divided by 2 pi theta whole raised to power 2 by 3. Discharge small q is equal to A into V is equal to 1 by n into r raised to 2 by 3 into s raised to 1 by 2. Taking capital N by small n is equal to 1. Proportional discharge is equal to small q by capital Q is equal to small a by capital A is equal to small v by capital V is equal to small a by capital A into small r by capital R raised to 2 by 3. Proportional discharge is equal to small a by capital A into r small r by capital R whole raised to 2 by 3 is equal to theta by 360 theta is equal to theta by 360 into whole 1 minus 360 sin theta divided by 2 by theta into whole raised to power 5 by 3. Partial flow diagram. Flow fluctuation occur in a sewer line, so it is always designed for partial flow. Crimp and Burgess had developed the following diagram for the calculation of hydraulic elements or sewers known as partial flow diagram. Partial flow diagram. Ratio of hydraulic elements small a by capital A, small r by capital R, small v by capital V and small q by capital Q. OL P1N ratio small d by capital D. This is small q by capital Q for variables and d by small n. Small q by capital Q for nd by n is equal to 1.0. This one is the curve for that. Then small q by capital Q for variable nd by small n. This one is the curve for that. Then small v by capital V for variable and d by n. This is the curve for that. Then small r by capital R. This one is the curve for that. Then nd by n. This one is the curve for that. Then maybe small a by capital A. This one is a curve for that. Then small r by capital R. Then hydraulic elements of circular sewers running partially full. Then small d by capital D 1.00, small a by capital A 1.000, small v by capital P 1.000, small r by capital R 1.000. For capital N by small n is equal to 1.0, small v by capital V 1.000, small q by capital Q 1.000, capital N by small n 1.00. For variable capital N by small n, small v by capital V 1.000, small q by capital Q 1.000. Then small d by capital D 0.90, small a by capital A 0.949, small v by capital P 0.795, small r by capital R 1.192, small v by capital V for capital N by small n is equal to 1.0, 1.124, small q by capital Q for capital N by small n is equal to 1.0, 1.066, capital N by small n 0.94. for variable capital N by small n, small v by capital V, 1.057, small q by capital Q, 1.002. This is the shapes of sewers, like that. Selection of shape of sewer based on self-cleansing velocity in DWF, based on structurally safe and stable. Selection of shape based on sufficient freeboard in maximum discharge. Selection of shape based on easy cleaning and maintenance. Classification: circular sewer. This one is a circular sewer. Circular sewer advantages: easily manufactured, gives maximum area for given perimeter, most efficient since it gives greatest hydraulic mean depth when running half or full, economical since it utilizes minimum quantities of materials, less settlement of deposits due to uniform curvature. Disadvantages: self-cleansing logic can't be maintained at DWF conditions in combined system. Suitable only when variation of discharge is not large. Small d by capital D 1.0, small a by capital A 1, small b by capital B 1, small q by capital Q 1, small d by capital D 0.9, small a by capital A 0.949, small v by capital B 1.124, small q by capital Q 1.066. Then small d by capital D 0.8, small a by capital A 0.858, small e by capital V 1.140, small q by capital Q 0.988. This is non-circular sewer. These are non-circular sewers. For example, here it is semi-elliptical.